NeuroImaging in BPM in 2019 with the key topic of correlation between smartphone addiction and psychosocial factors among students and assessment of fMRI brain activation in response to reward. Let's view the video recording of Nisha, Syed, Nasser on the topic neuroimaging tools for processing functional MRI data.
Hello and a very good afternoon to everyone. I would like to thank the NeuroCoB Society of Malaysia for inviting me as a keynote speaker. My name is Nisha Syed Nasser and I'm currently working as a research scientist at Mahajan Imaging, New Delhi, India, where my primary focus of interest is neuroimaging. I'm here to talk about the neuroimaging tools for processing of fMRI data and will be showing you how to process the fMRI data using statistical parametric mapping. fMRI is a non-invasive neuroimaging technique that is used to determine the brain activity during blood oxygen level dependent imaging. Bold imaging, it completely relies on the difference in the magnetic properties of oxyhemoglobin and deoxyhemoglobin. That is, like whenever you perform a task related to memory or cognition, the neuronal activity in that brain area which is very specific to that particular task increases. So due to the increased neuronal activity, there is a surge in the blood flow to that particular brain region, which can be determined using the bold imaging. So there are different tools which are used for processing of fMRI data. So the statistical analysis, they are mainly used to identify the regions of the brain that show significant changes in the activity in response to a particular task. So there are different tools that are available to process the fMRI data, some of which includes the AFNI, the statistical parametric mapping, FSL, FreeSurfer, Micron, and the BrainWorker. So the most commonly used application for processing of fMRI is a statistical parametric mapping. It is an offline MATLAB based application. It is a very powerful tool for analysis of fMRI data, and it provides a very comprehensive and a sophisticated approach to study the brain activity. So the main aim of fMRI data analysis is to determine if the cortical brain regions where the signal changes occur during the presentation of a cognitive task designed to a specific brain function. There are three main stages that are involved in analysis of the data from any fMRI experiment. First is pre-processing, which involves steps for removing the noise, the patient motion. The next step is the general linear model. The third is the results which are displayed using maps of T statistics. So there are 9 steps which are involved in processing of fMRI data using SPM. The first step is DICOM import. The second is slice timing. Third is realignment. Fourth is co-registration. Fifth is normalization. Sixth is smoothing. Seventh is model specification. Eighth is estimate. And the final is the results. So I'll just show you how to perform every step in detail. The first step is DICOM import. To proceed with any fMRI data, you need to convert the DICOM files to the Nifty files, which can be done using the DICOM import. Open DICOM import, or click on the DICOM files and navigate to the folder where you have all the patient specific DICOM files. Let it be T2-weighted images or bold imaging. Just choose a folder which has all the patient DICOM files. Right click it and select all. Then click on directory structure and choose output directory, patient ID and structure time. This will sort all the DICOM files as per the series name. Click on output directory and choose the directory where you want to save your Nifty files. Then click run. After DICOM import, we continue with slice timing. So we input all the Nifty data specific to fMRI. Click on sessions, navigate to the directory that has the Nifty files. Right click and choose all. Number of slices. To check the number of slices, TR in slice order, just go back to your Nifty file and choose the fMRI series, and you'll be able to see a notepad containing the information. From there, you'll be able to identify the number of slices and the TR and the slice order. The slice order is specific to the scanner. In the scenario, we are using a GE scanner, and the slice order here is interleave bottom up. So key in all the necessary values, and after slice timing, all the files will be saved with the prefix of A. So once you have keyed in everything, just save the slice timing file to the work directory and you can run it. After slice timing, we continue with realignment. During the patient scanning, the patient would have moved inside the scanner. So even small head movements can cause movement artifacts, so which may add up to the residual variances and reduce sensitivity. So we need to do realignment to correct for patient motion. So after slice timing is completed, click on realignment, estimate and reslice. Click on data, click on sessions, and choose the files that have undergone slice timing, that is the slice files with the prefix A. Right click, select all. Then go to number of passes. From register to main, choose it to register to first. Save the registration file to the work directory where you have saved the slice timing file, and you can click run. After realignment, we continue with co-registration. So co-registration, it allows the subject's own T2 weighted images to be overlaid onto the functional image series. So to do this, click on co-register, estimate and reslice. Click on reference image, go back to the raw folder where you have the fMRI files. Click type mean and choose the mean image. Click OK. The source image is the patient's T2 weighted anatomical image. You can choose the Bravo or MP-Rate sequence depending upon the scanner, and click save. You can save the job to the work directory where you have saved slice timing and realignment. Once it is saved, you can click run. After co-registration, we continue with normalization. So during normalization, we average the signals across the brain so that the brain images are roughly wrapped to the same space. In this scenario, we are normalizing the brain to the MRI template. So click on normalization, estimate and write. Click on data. Click on image to align. go back to your raw data. In the source image, you can choose the Bravo image that has been co-registered, and now click on images to right. These images will be your realigned images. Go back, you have to choose the registered realigned images from the fMRI series raw folder with a prefix of RA, meaning they have undergone realignment and slice timing. And voxel sizes, the voxel sizes are scan specific. You'll be able to identify the voxel size from your scans. Once everything has been manually entered, you can save the job to the work folder and you can run it. So after normalization, we go to smoothing. So the functional images, they need to be smoothened prior to the statistical analysis so that the corresponding sites of activation from different brains are superimposed. Click on smoothing. Click on images to smooth and go to your raw directory. Click on your fMRI speech tab and choose the file with the prefix WRA. Right click, select all. Now click on full width half maximum. It is supposed to be twice your voxel size. So once all the values have been keyed in, save the job to the work folder and you can run it. After smoothing, we do the model and estimation. In this, the GLM is used to specify the different conditions such that the blocks in the form of a design matrix, which will help us define the experimental task and the nature of the hypothesis that we are testing. Click on the directory where you want to save your .spm file. I'm just saving it in the raw fMRI file where I have all the fMRI Nifty files. So units for design, you can choose as scans. Interscan interval is your TR value and the other parameters are default. Click on data and design. Click on scans and you can choose your smoothened images with a prefix of SWRA. Right click, choose all. So conditions. So the conditions depends upon the nature of your task. Suppose if you're having one condition, you just have to click it once. If you're having multiple conditions, then you need to replicate the conditions every time. In this scenario, I'm having only one condition, that is just a speech task. So I'm just naming it as speech. Click OK. The onsets, it refers to a block design at which volume the scan was performed or the task was being given to the patient. So we can just key in the values. These values are completely dependent upon your task. It depends upon your TR value and the number of volumes and the duration of the task. So the durations are in volumes. So other parameters are kept default. You can save the .mat file uh, in your directory, and you can click run. So this is the statistical analysis design where we can find the speech task highlighted here, interleaved with rest blocks. So after the first level analysis, we will have to do the estimate. Just click on the folder, go navigate to the directly and choose your .mat file and click model estimation, and it's done. The final step is the results. So the neuronal activity in response to an experimental task is obtained by specifying the linear contrast, that is either the T contrast or the F contrast. So to do this, you have to click on results and go back to the directory which has the .mat file. Click on it, done, okay. Go to T contrast, type the name of the contrast. Here we are having only one experimental condition, that is a speech. So I'm just typing speech. And if you want to see the region of the brain activated during the speech task, you have to give speech the value of 1. Click OK, click done, apply masking none. We usually adjust the p values to FWE. So the FWE is the family wise error corrected method, which controls for a 5% chance of a single false positive. So usually the multiple comparison correction is controlled for family wise error rate, and you can enter a p value of 0.05. Extent thresholds more than 0. So you'll get to identify the regions of brain that are getting activated during the speech task. So here you'll get to know the coordinates and everything. So we have an inbuilt atlas. You can just right click on the voxels and you'll be able to identify or see the region of the brain that is activated. So we also have the WFU pick atlas, which can be used uh, to to label the brain regions that are activated in a particular task. Thank you, everyone. This was a small and a very brief hands-on session about how to process an fMRI data using SPM. I hope I hope the session was very useful, and I hope to see you all in person soon so that we can have an hands-on experience, and I would be more than happy to take your questions and answer them. You can feel free to reach out to me on my email ID, and I would be happy to answer all your questions. Thank you so much, and thank you NeuroCoB Society for giving me an opportunity to present my work. Thank you.
Thank you.